Transient analysis. Okay, in this transient analysis, for example, this is the one question. So this question we have to execute, we have to verify the results by using PSPAS. Okay, in this example, to, to simulate and study the transient response of a series RC circuit using MATLAB or PSPAS. Okay, so in this example, I will execute by using PSPAS, where R is equal to 200 ohms and C is equal to 10 microfarads for the following conditions. So first condition is called source voltage is 40 volts DC with all initial conditions set to 0. Okay, initial conditions, that means capacitor voltage across the capacitor, V of 0 is equal to 0. Okay, and the voltage source is called 40 volts. Okay, this is the case 1. And case 2, source voltage is a pulse signal with a period of 0 seconds and pulse width 5 milliseconds and rise and fall times are 1 microseconds. Amplitude is called 20 volts and initial value is called 0 volts. So these are the different conditions. By taking these conditions, we have to execute uh, say example in piecewise. Okay. So first case 1. So V of t is equal to 40 into U of t DC voltage source. No? That's why. So we have to take like this. Y of t is equal to 40 into U of t and then convert into Laplace transform S domain. V of s is equal to 40 by s. And then I of s is equal to, so we know I is equal to V by R. Okay, in series R circuit, this is the expression. Okay, SC divided by RC into S plus 1 by RC. So V I is equal to V by Z. So V is called 40 by S. Okay, and then modify this expression, we will get 40 by R into 1 by S plus 1 by RC. So taking inverse Laplace transform on both sides, and then I have t is equal to 40 by R into e power minus 1 by RC into t. Substitute R is equal to 200 and C is equal to 10 microfarads. R is equal to 200 and C is equal to 10 microfarads. So in this equation, then you will get I of t is equal to 40 by 200 d power minus 500 into t. T is called time constant e power minus t by 1 by RC. RC is called time constant. Then you will get like this expression. And then at t is equal to 0, by substituting t is equal to 0, so e power 0, 0. That's why 40 by 200, that is equal to 200 milliamps. Let I of t is equal to, that is called I of 0. Okay, at t is equal to 0, this is the current, 200 milliamps. And at t is equal to infinity is called steady state. So e power minus infinity is equal to 0. That's why I of t is equal to infinity is nothing but I of t is equal to infinity, 0. Okay. So then at time t is equal to time constant is called RC, 2 milliseconds. Okay. Then I have t is equal to 200 times of 37% means this is called time constant. Voltage across the capacitor exponentially and other exponentially increases. Okay. And current across the capacitor exponentially decreasing. Exponentially decreasing, current exponentially decreasing. That's why 36.7%, approximately 37%. Okay. So this is the time constant. So 200 times 37%, 37% of 200 milliamps in current. That's why how much time is required per time constant? 74 milliamps. Okay. So the voltage drop across the resistor R is called VR of t is equal to I of t into R. Then I of t is equal 40 by 200 into e power minus 500 into t to 200. 40 into e power minus 500. Then at t is equal 0, 0, VR of t is equal 40 volts. At t is equal 0, at transient condition, capacitor does not allow sudden changes in voltage. That's why it's short circuit. Okay. That means the voltage across the resistor is nothing but source voltage. Under steady state condition, capacitor is acts as a open circuit. That's why current 0, then voltage drop across the resistor is equal to 0. V is equal to I into R, I is equal to 0. That's why under steady state condition, I is equal to 0. So under steady state condition, t is equal to infinity, I of t is equal to 0. Then VR of t is equal to I of t into R. Then this is also 0. Okay. Then, so this plot will get like this. This is called I of t. So exponentially decreasing. This is called time constant, 37% according per particular one time constant. So we'll get 74 milliamps, exponentially decreasing. So this is the current expression. Okay. And then voltage across the resistor. Voltage across the resistor is also exponentially decreasing. So at starting condition, transient condition, capacitor short circuit. That's why. So maximum voltage across the resistor is nothing but 40 volts. Voltage across the resistor and source voltage both are same during transient condition. That's why initially at t is equal to 0, the voltage across the resistor is called 40 volts. Then exponentially is decreasing this way. Okay. This is called a voltage VR of t expression. And then VC of t, voltage across the capacitor, V of t minus VR of t, that is equal to 40 into 1 minus e power minus 500. This is called, one is called steady state and this is called transient condition. Then voltage across the capacitor, VC of t, is increasing, exponentially is increasing. Finally, the voltage across the capacitor is called 40 volts, that is called source voltage. Under steady state condition, capacitor acts as open circuit, that's why. So whatever the voltage present across the source is nothing but our source voltage, voltage across the capacitor. This is for case 1. And case 2, by taking V of t is equal to 20 into U of t minus U of t minus 1. Okay. So that is nothing but, so V of s is equal to 20 by s, that is into 1 minus e power minus s. It's clear? Then, so this expression can be modified like this. I of s is equal to V of s by z, z of s. Then this equation can be modified like this. So by substituting the R is equal to 200 ohms and C is equal to 10 microfarads, and then we will get like this: T is equal to 0, I of T is equal to 20 by 200, then 100 milliamps. And under steady state condition, T is equal to infinity, then I of T is equal to 0. Okay, then voltage drop across the resistor is called VR of T is equal to R into I of T. Then substitute this all values, then we will get VR of T is equal to 20 into e power minus 500 into T, V of T minus e power minus 500 into T minus 1 into of T. So this is the expression across the resistor. And then by substituting the T is equal to 0, then VR of T is equal to 20 volts in this equation. And the substitute T is equal to infinity and VR of T is equal to 0 volts. Then finally the voltage across the capacitor is called VC of T is equal to V of T minus VR of T. Substitute these all values V of T and VR of T, and then we will get this type of expression. In this set T is equal to 0, VC of D is equal to 0. By substituting T is equal to 0 in this expression, so we will get VC of T is equal to 0. T is equal to infinity is also VC of T is equal to 0. Okay. And then at T is equal to T, that is called 5 millisecond, VC of T is equal to 18.36. 5 milliseconds. Okay. So for 5 milliseconds, the voltage across the capacitor is called 18.36 volts. So this can be verified by using manually by using PSpice. Okay. So first we have to connect the circuit same as it is by using PSpice. Okay. Go to PSpice and take one voltage source VDC, place here, and then take one switch, close switch, T close, place here, T close, and take one resistor, and similarly take one capacitor, controller. So, and also one ground, connect first elements, these elements by using wire, connect this like this. Okay. So this is the circuit. The voltage is nothing but first condition, case 1, the voltage is called 40 volts. Okay, 40 volts. And the next T close, okay. And here what is the resistance is called 200. Value of R is equal to 200. 200. And capacitance C is equal to 10 microfarad. 10 microfarads. 10 UF. 10 UF. 10 microfarads. And also initial conditions 0. This IC is equal to, IC is nothing but initial condition, that is equal to 0 volts. Initial conditions is equal to 0. And connect one ground also here. One ground, place here, and connect ground like this. So after this, go to analysis, set up transient, enable transient, and print step is equal to 0 nanoseconds, and the final time is called, for example, 20 milliseconds. 20 milliseconds, and then okay, close. And connect one voltage marker across the capacitor, then we will get how voltage changes across the capacitor. Connect one voltage marker across the capacitor, and the color of the voltage marker is color, for example. So then after this, simulate, then transient, transient example. Okay, so like this, exponentially increasing. The voltage across the capacitor is exponentially increasing. This is the expression. Okay, voltage across the capacitor is exponentially is increasing now. It's clear. So in this example, first case, the voltage across the capacitor Vc of t is increases exponentially. Okay, so that is verified by using PSpice. Exponential is increases to up to 40 volts. Maximum source voltage is called 40. That's why capacitor increasing the voltage like this. Okay, similar way, and here in the circuit for second case, what is the second case? Second case, source voltage is called pulse signal. Source voltage is called pulse signal, and here source voltage is called pulse signal, and a period of 0 second, with a period of 0 seconds, width of 5 milliseconds. Okay, delay time 0 seconds, and width, pulse width is called 5 milliseconds, and rest time and fall time is called 1 microseconds. Okay, so in this circuit, instead of 40 voltage source, delete here, and from from library take V pulse. V pulse. This place here, close this. Then after that, here in this by pressing 2 times, V1 is equal to 0. Here V1 is equal to 0 and V2 is equal to 20 volts. Like this we have to take. Enter V1 is equal to 0 volts. Say what? And V2 is equal to pulse signal 20 volts. That means 0 to 20 volts increases. Say what? And delay time is equal to 0 seconds. 0 seconds. And rest time 1 microseconds. Rest time and fall time are both are same. Okay. Rest time 1 microseconds, 1 microseconds. Fall time is also 1 microseconds. That's the cycle. And after this, next pulse width. Pulse width is equal to 5 milliseconds according to question. 5 milliseconds pulse width. Okay. Here pulse width is equal to 25 milliseconds. And rest time fall time 1 microseconds. Okay. Pulse repetition 0. Okay. Pulse repetition 0 seconds. save alter. Okay. Analysis. After that, analysis. Setup. Transient. Here take 16 milliseconds. 16 milliseconds and okay, close. And connect here across the resistor. First we have to observe the waveform across the resistor. Okay, connect one voltage marker and place on here. Okay, and then run like this. This is the generator. So 0 to 20 volts, and then decreases like this. So okay, and in this case, first we have to understand the how voltage across the resistor is changes. Here, connect one voltage marker, then what type of output we will get. Okay, first we have to observe the what type of input. What is the signal generated from P space. Okay, and then run, and then it will open. So like this, this is our signal according to the question. Okay, so pulse signal out delay time is equal to 0 seconds and pulse width is equal 5 milliseconds. Pulse width is equal to 5 milliseconds. This is called pulse width. Pulse width is equal to 5 milliseconds. That's why here 0 seconds to 5 milliseconds. This is called pulse width. Okay. Rise time and fall time are very, very less, microseconds. And pulse width is, this is the pulse. Pulse repetition is 0. That's why the waveform is not repeating. Okay. This is the our input voltage waveform, pulse signal, and delete this, and then one place one marker. Okay, current marker and resistor. How current is changes in series. How this current changes we have to observe. Okay, we have to understand this how current is changes, current wave. And then run icon, and then current changes like this. Current is exponentially is decreasing in this way. Okay, exponentially is decreasing. So 100 milliamps to 0 amps. Okay, 100 milliamps to 0 amps. This way the current is decreasing. Okay, so here enable toggle cursor and place, this is called what is this, x-axis. This is called 1.059 milliseconds. Okay, so like this, and mark like this. So this is the expression. Exponential is decreasing. Okay, and finally settle to 0. The current is changes 0 to 5 milliseconds. Our pulse width is called 0 to 5 milliseconds only. So that's why the current is slowly is decreasing exponentially. Okay. Then connect one voltage marker across the capacitor. Here, the voltage across the capacitor by connecting like this, and then run, and then open like this. Properties, pulse width. So voltage across the capacitor exponentially is increases up to 5 milliseconds because of our source is present only 5 milliseconds. So pulse width it is equal to pulse width is equal to 5 milliseconds. Na? So that's why the voltage across the capacitor exponential is increasing in this way. And then the source is turned off after 5 milliseconds. That's why this exponentially decreasing voltage across the capacitor. Okay. So this is called voltage expression across the capacitor. Up to 5 milliseconds, it is increasing. Up to 5 milliseconds, it is increasing. And after 5 milliseconds, it will be exponentially decreasing. Okay, understood. So for this case 2, the up to 5 milliseconds. So what is the voltage here? 5 milliseconds. T is equal to 5 milliseconds. What is the voltage? 18.36. So 18.36. So here what is the voltage means how to find this enable toggle cursor and the marker here. So 4.99 is nothing but 5 milliseconds. The corresponding uh, voltage is called 18.36. Up to capacitor will charges to 18.36 for 5 milliseconds, and then exponential is decreasing in this way. After 5 milliseconds, this source is turned off. Okay, so that means by connecting one voltage source here, simultaneously both will display like this. If you are one voltage marker connected, okay, then run, okay, and enable proper this width of the pulse signal is changes like this, and this is our input. Red color is called our input. So this is the input. Okay. So up to 5 milliseconds, this voltage source is present. Okay. Up to 5 milliseconds only this source is present. After 5 milliseconds, source is disconnected. I mean turned off up to here only. So that's why up to here the capacitor charges up to 5 milliseconds. After this, capacitor is exponentially decreasing. Okay. So in this way we have to analyze the voltage across the capacitor. Okay. Then how the voltage across the resistor is changes. So capacitor voltage exponential is increasing, and similarly the voltage across the resistor is exponential is decreasing. Okay. So to identify the voltage drop across the resistor, so go to markers, mark difference, mark voltage difference. So one place here one difference and place another difference plus minus. Okay, and then run simulate. Exponentially decreasing we will get, and also one take voltage marker in between source across the source, and then run, and then it will be up here like this window. So this is our source voltage. Okay, source voltage waveform, and this is called voltage across the voltage drop across the resistor pulse width. Okay, exponentially decreasing. Here 0 to 5 milliseconds source present. Okay, and the voltage across the exponential is increasing. During this transient condition, uh, capacitor will act as a short circuit. That's why maximum voltage appear across the resistor at t is equal to 0. Finally, the voltage across the capacitor is increases, and capacitor will act as open circuit, and the voltage drop across the resistor is exponentially decreasing, exactly opposite to the capacitor. So like this, in this way we have to analyze the transient response of series RC circuit.